Dear students, yesterday we studied about continuity and distant differentiability. We studied definition of continuity and solved some problems. Today we continue this chapter. Continuity. Once again I recall the definition of continuity. Continuity or the function is continuous. The function f is continuous at a given point. At a given point at x equal to a. At x equal to a, then limit of x tends to a minus f of x, which is equal to limit of x tends to a plus, which is equal to f of a. It is left hand limit and right hand limit, and the value of the function at x equal to a. These are equal or these are coincide at x equal to a. Then the function is continuous at x equal to a. It's the f is continuous at that point only. It is continuous. I told another definition, which is continuity. The function is continuous function. The function f of x is continuous. It means it continuous everywhere. The function is continuous at any point of domain of f. Domain of f. The function is said to be continuous function. Continuous function. If it is continuous at every point or every point in the domain of f. The function is said to be continuous function if it is continuous at every point in the domain of f. The function should be defined here. Then only we get the continuity of the function. We studied in the previous class the modulus functions are continuous. Modulus function is on real number is continuous. Modulus function is the graph of the function is like this, because plus 2 is plus 2, plus 1 is plus 1, minus plus 2 is plus 2, then plus 3 is plus 3 here. Then here also minus 1 or minus 2, it's minus plus 2. Therefore, the graph of the function of modulus function f of x is equal to mod of x on real number. Here, domain of the function f of x is real number. Here, the graph of the function is everywhere, it's continuous. On the real line, the function is continuous. Here, we can draw the graph without lifting the pen or pencil. In one stroke, we can draw the graph of this modulus function. In the last year, we studied many functions like constant functions, identity function, and polynomial function, etc. Today, identity function. Identity function. We discuss about identity function. Here, identity function means f of x is equal to x. Here, f of 1 is equal to 1. F of you studied in the last year. This graph also, this graph. Therefore, here also the function is continuous. We can find the limit of x tends to 0, x tends to a. A is any real number. Then f of x is equal to limit of x tends to a, which is x, therefore is equal to a. Then f of a also is equal to a. Therefore, the limit of the function and value of the function are also equal. Therefore, the function is continuous. In the same way, we can prove the constant function. Constant function. Here, constant function f of x is equal to k or c. F of x equal to k or c. K is any real number. Here, the constant function is the graph of the constant variable is like this. If k is equal to 3, it's k. If it is equal to 3, the 3 is the line parallel to x-axis. The constant function also continues. If we take the limit of the function, if it does not change the value of the k, it becomes the same. F of 1 also is equal to k itself because there is no k variable here. Therefore, f of 1 also k, f of 2 also k, like this. Therefore, the constant function is also continuous function. Consider a polynomial function. Every polynomial function is continuous. Here, the example, I think 6. Every polynomial function is continuous. You studied already the polynomial function. Consider a polynomial function. Consider a polynomial function. F of x equal to a0 plus a1x plus a2x square plus a3x cube plus an x to the power n. Here n is always positive, n is positive or non-negative number. Positive number or non-negative number, then a0, a1, a2, a3 are real numbers. Then f of x, limit of f of x tends to c, any constant c is a real number. Then limit of x tends to c, a0 plus a1x plus a2x square up to plus an x to the power n. Then we take the limit a0 plus a1c plus a2c square up to plus a n c to the power n. A up to c to the power n. We take the value of the function at c is also equal to a0 plus a1c plus a2c square up to a3c cube plus up to an c to the power n. Therefore, the limit of the function x tends to c f of x, which is equal to f of c. Limit of the function and the value of the function at c is equal to 0. Therefore, the function is continuous. Therefore, every polynomial function, it's not this polynomial, every polynomial function is continuous. If it is taken as x square plus 2x plus 3, it's the polynomial function, but it is, you can check the function is continuous. Before checking the continuity, you should know about it is continuous or not. Yeah, and therefore I discuss the continuity of the some functions. I told identity function, polynomial function, and constant function, modulus function, all are said to be continuous functions. Next, trigonometric functions. Trigonometric functions. You already know about f of x equal to sin x. Sin x is a trigonometric function. You already studied about the graph of this function. 0. This is 1. This is minus 1. Then pi by 2. Pi by 5 minus 3 pi by 2 plus 3 pi by 2, etc. Here also minus pi by 2 minus 5. The graph of the function is sin 0 is 0, sin pi by 2 is 1. The graph is like this. You studied in the first period. Here, the graph is continuous. We can draw the graph with one stroke. Therefore, the function is continuous. So, we can prove that also. Limit of x tends to a. A is an real number. Then, sin of x is equal to sin a. Then the f of a, it also sin a. Therefore, the function is continuous. Limit of the function and the value of the function at a or any real number, its function is continuous. Then we can prove cos x also the same way. We can prove the cos x also. Cos x, graph of the cos x graph is here minus 1 pi by 2 pi plus minus pi by 2 plus minus 5. Here the graph 0 is 1. Pi by 2 is 0. Here also the function is continuous. F of x is equal to cos x graph is continuous. We can do this. Therefore, we can say all trigonometric functions are continuous, you can check tangent function and cos function, tangent and cosec sec. Also, when it is defined, then only we can prove the other trigonometric functions said to be continuous or not. If they are defined, then only we can prove the function is continuous. Now, we study some algebraic or algebra of continuous function. What is algebra of continuous function? Algebra of continuous function. Here is there. Theorem 1. Suppose f and g are two continuous functions, f and g be two continuous functions two real functions and continuous at real numbers c. Real number c. Then suppose f and g are two real functions or real valued functions. It means domain of the f is function is real numbers. Domain of the function is real number and continuous at real number c. Then 1 f plus g. F plus g is continuous at x equal to c. Then second, f minus g is continuous at x equal to c. Third one, f into g is continuous at x equal to c. Fourth one, f by g is continuous at c, but g of c not equal to 0. Provided it should be provided it is in the denominator g of c should not equal to 0. Then only the f by g is also continuous at c. Yeah. Once again I say, suppose f and g be two real functions and continuous at real number c, f plus g is continuous at c and f into g also continuous at c and f minus g also continuous at c and f by g also continuous at c, but provided g of c is not equal to 0. We solve some problem here or proof one proof is I will give you one proof. Continuity of f plus g at x equal to c. Clearly, it is said that it is defined at c. Then only we can find the continuity. F plus g, continuity of taking the f plus g at x equal to c. Clearly it is defined at c. At x equal to c. We have limit of x tends to c, f plus g is equal to limit of x tends to c, f plus limit of x tends to c, g, which is equal to, f plus g means I take function here also. Then this is the function f of c plus it's g of c. Then we take a f plus g into c. The function is continuous. F plus g plus c into c is continuous here. Or in the same way, we can do f minus g. Here minus, there minus, here also. We can throw again f into g. Here also into, here also g. F into g. Also continuous functions. It's the algebra of continuous function. Sometimes two functions are added, subtracted, or multiplied or divided. Then also we can prove the functions are continuous if the individual functions said to be continuous at that point. Then only we prove that the product of the two functions or addition of the two functions and subtraction of the two functions, a division of two functions, if denominator should not be equal to 0. Which should be provided here, then only we prove that the functions are continuous. Now, we do one problem. Example. Sorry. Prove that every rational function is continuous. Function is continuous. Rational function. You already studied in the first video. Rational function is given by p of x, f of x equal to p of x divided by q of x, but q of x should not be equal to 0, provided q of x is not equal to 0, where p and q are polynomial functions. Polynomial functions. Domain of the function is domain of the function should be defined here. It's where it is equal, q of x is equal to 0. That point is except that point. Therefore, domain of the function is all real number except the point at which q is 0. At which the points at which q of x is equal to 0. Where q is 0. Where q is 0, that point is derivative. Then only we can take the domain of the function. In all the other points, the function is continuous except the q of x pair is 0, then only that point is discontinuous. That can define that point. Therefore, we can prove here p and q are polynomial functions. I already told polynomial functions are included also. Polynomial functions are continuous. Therefore, p by q. Once again, I recall p by f. P and q are polynomial functions. They are continuous. P and q are continuous at given point, at real number given point at A is a real number. Then P by Q also continuous, because individually P and Q are continuous functions. By algebra of the functions, continuous functions, P by Q also continuous function. By theorem 1, we can prove, we can prove the rational functions are continuous functions. Now, we shall solve some problems in 5.1 exercise. One more theorem is there, theorem 2. Theorem 2. If f and g are two continuous functions are the real value, first real value or real functions, real valued functions such that the composition f naught g is defined at A, if G is continuous, at A and F is continuous at G of A, then F naught G is continuous at A. If f and g are two real valued functions, such that f naught g is defined at A, we can define f naught g also. If g is continuous at A and f also continuous at g of A, then f naught g is continuous at A. Then f naught g also at composition, f naught g also continuous at A. Here we can solve one problem here by using this. Show that the function defined by f of x equal to sin of x square is continuous function. The function is defined every real number. The function is defined every real number. The function f is composition of G naught H of two functions G and H. We take G of X and H of function as G of X is equal to sin X and H of X is equal to X square. Here the function is defined. Every real number, the function f is composition of two functions. Here two functions. Sin of X square. It is sin X and X square is not here. Sin of X square. We take it as the function f is composition of G naught H. Therefore, two functions are G and H. G of X is sin X and H of X is X square. You studied in the composition of functions in the real functions also. Then, here G of X is equal to sin X. G and H are continuous functions. Yeah? G and H are continuous functions because G is a sin X. G of X is sin X function. It is trigonometric function. Therefore, it is continuous. I already told. H of X equal to X square. It's polynomial function. It's a polynomial function. I already solved this problem in the previous class also. G of X is sin X is a trigonometric function, is continuous, and H of X square is a polynomial function, is a continuous function. Therefore, I write it as G and H are continuous functions. Continuous functions. By theorem 2, G naught H of X, which is equal to G of H of X, which is equal to H of X is X square. Then G is equal to sin of X square. This continuous function, which is equal to f of X. G naught H of X is equal to G of H of X. You study with the relational functions. G naught H of X is equal to G of H of X is equal to G of X square. G is sin of X square. Therefore, it is equal to f of X. The function, the composition of the function is continuous. If the singular f and g are real and they are continuous, then the composition of the function is also continuous. If it is defined. Now we solve some problems in 5.11 exercise. 1. Exercise problem. I don't solve all the problems, but I take some important and different problems. Through that, the function f of x is equal to 5x plus 3 or minus 3 is continuous. continuous at x equal to minus 3. At x equal to minus 3. Here, first we take the limit and find the value of the function at x equal to minus 3. At x equal to minus 3, f of x is equal to 5x minus 3. You learn the steps. At x equal to minus 3, first you find that f of x is equal to 5x. This is the function. It's the function. We put the value of minus 3 in the function. We replace the value of minus 3 by x. Replace x by minus 3 or substitute the value of x. Minus 3 minus is equal to minus 8, 15 minus 3 which is equal to minus 18. Then we take the limit of the function x tends to minus 3. Here 5x minus 3. We already studied in previous class limit of the functions. It's a polynomial function. You can put the value here also 5 into 5 minus 3 minus 3. Therefore minus 15 minus 3 is equal to minus 8. Therefore here limit of f of minus 3, limit of x tends to minus 3, f of x is equal to f of minus 3. Therefore the function is continuous at x equal to minus 3. Here given point at minus x equal to minus 3. Sometimes we will take a q x equal to minus 2 or x equal to plus 2 or x equal to minus 1. You put the value here minus 5. You can get the continuity at that point, continuous or not, or discontinuous. Yeah, find that continuity. Many problems are there. The same way you can solve. I take another problem. Second example, f of x equal to x square minus 25 divided by x plus 5, x is not equal to minus 5. Here, f of x is rational function. It's a rational function because it's a two polynomial functions. P of x is equal to x square minus 25 and p of x equal to x plus 5. Two functions are there and the denominator x plus 5 is not equal to 0. Therefore, provided x, if it is minus 5, the denominator is 0. Therefore, provided the domain x is not equal to minus 5. Real number set there is no function whose domain is real number minus 5. Real number minus 5. Real number set करके it is minus 5 not there. All real number set is a domain of this function, but minus 5 is left. Then let a be any point of the domain. A is not equal to minus 5. but you can take other value. Then we take the limit of the function x tends to a f of x, which is equal to limit of x tends to a x square minus 25 divided by x plus 5. You already studied in the previous class, taking the limit here. We write the x square minus 25 by using the formula x plus 5 and x minus 5. Then x plus 5. X tends to minus 5. X plus 5 gets cancelled. Then you put the value of a. Then a minus 5 is the answer. We can put the value of a f of a. F of x equal to x square minus 25 divided by x minus x plus 5. Here also we put the value a square minus 25 divided by a plus 5. We can get a plus 5 and a minus 5. Again a plus 5 gets cancelled. You can get the value a minus 5. Therefore here limit of the function x tends to a f of x, which is equal to f of a. Therefore the function is continuous at every real number in the domain of f. Therefore the function is continuous at all points in the domain of f, because in the domain minus 5 is not there. I solve one more problem here. Taken marks materials. Go to 1. Discuss the continuity of the function. Discuss the continuity of the function f defined by f of x equal to x plus 2 if x is less than or equal to 1 and x minus 2 if x is greater than 1. Here the function is defined at all real number lines because that x is less than or equal to 1, x plus 2, 1 less than or equal to 1. Then greater than 1 also, the function is x minus 2. Therefore, the function is defined every point of the real line. Solution. The function is defined at all points of the real line. In case 1, here we have to prove the continuity at every point less than 1, greater than 1 and equal to 1. Then only we can prove it is a continuous function everywhere. Case 1, if c is less than 1, c is any real number, it's less than 1. Less than 1. Then f of c is equal to Here f of x is equal to, I will write here, f of x less than 1 is function is x plus 2. Therefore, f of c is equal to c plus 2. Then the limit of the function x tends to c, x plus 2, which is equal to c plus 2. Here, limit of the function x tends to c, f of x is equal to f of c. Therefore, the function is continuous. Therefore, the function is continuous and c is less than 1. Means the all real numbers less than 1. Less than 1. Means here is 1. The function is continuous less than 1. Now we check the continuity for case 2. If c is greater than 1, then f of x equal to, here, greater than 1, x minus 2. Then f of c is equal to c minus 2. Then f of x, limit of f of x tends to c, which is equal to limit of x tends to c, x minus 2 is equal to c minus 2. Here also, limit of x tends to c, f of x, which is equal to f of c. Therefore, the function is continuous. The function is continuous at c is greater than 1. Now we have to show the function is continuous at c is equal to 1. At c is equal to 1, we have to find the value x plus 2 here. Then the function x equal to 1. Here x equal to 1. At x equal to 1. It means x is equal to 1. I will take the real number c is equal to 1. Therefore, is this less than 1? No, therefore we take it as c. It's x equal to 1. Therefore, f of x equal to, it's 1 equal to 1 is here. Therefore, x plus 2 is the function. If the equal to sign is here, the f of x will be taken as at x equal to 1 is x minus 2. Here there is an equal sign, therefore we will take the f of x equal to x plus 2. Then f of c is equal to 1, f of 1 is equal to 1 plus 2 is equal to 3. Then limit LHL, which is equal to limit of x tends to 1 minus f of x, which is equal to limit of x tends to 1 minus. Here we taken 1 is greater than 1, it's less than 1, therefore we take the next x plus 2 is the function x plus 2, which is equal to 1 plus 2, which is equal to 3. Then RHL limit of x tends to 1 plus f of x, which is equal to limit of x tends to 1 plus, here x minus 2. Here is 1 minus 2 is minus 1. Here LHL and RHL are not coincident here. Therefore, LHL is not equal to RHL. Therefore, the function is discontinuous. The function is discontinuous. Function is discontinuous or not continuous. The point of discontinuity is 1. The point of discontinuity is 1. That is the point of discontinuity of the function is 1. We draw the graph of this function also. Here, first in this problem, we should solve all the cases. C is less than 1 and C is greater than 1 and C is equal to X is equal to 1. In all the point of the function, we should prove the continuity of the function. Here, case 1, case 2, the function is continuous, but in the case 3, if x equal to 1, the function is not continuous. Therefore, the discontinuity for it is x equal to 1. X equal to 1. We can draw the graph of this function. Here, 0, 1, 2, 3. Here also -1, -2, -3. Then +1, +2, +3. -1, -2, -3. Then -2 plus, because is less than 1, x plus 2, x plus 2. Here that -1 plus 2 is equal to +1, plus 1. X equal to 0, x equal to 0, it is less than 1. 0 plus 2 is 2, therefore the function is here. But the x is here. But at 1, the function is defined here, x 1 also, therefore x equal to 1, 1 plus 2 is 3. 1 plus 2 is 3. Graph of the function is like first. Then x minus 2, if it is greater than 1, x minus 2, f of x equal to x minus 2, here 1 minus 2, therefore it is equal to -1. If x equal to 1, it's -1. Then x equal to 2, it's equal to 0. Therefore the graph is like this. Here the point is this. Here it is included, but it is not included here. But the graph of the function is like this. Therefore, it is not continuous at x equal to 1. We can show the graphically also, we can show the function is not continuous. We cannot draw the graph in one stroke. Thank you.